Good morning. My name is Brandon Hernandez-Cano.
Hello, I'm Austin Frock.
Hello, my name is Justin Martinez.
I am Christian Robert Naj. AI is here and is changing tech and engineering in a big way. It's more capable than ever, but it still desperately needs workflows with guidance and structure to help control its unreliable behavior. So, our capstone project focused on exploring four fields, namely interaction, workflows, automation, and evaluation.
When people first think about using AI in game development, the default use case is usually script generation. You can ask the model to write C# for you, clean something up, or help build a new feature faster. This was the starting point for all of us going into this project, but I really wanted to explore what happened when the agent was given access to more than just a code editor. In my work, Unity MCP was what made this possible by letting the agent interact more directly with the development environment. It could work with scenes, use tools, modify editable fields, create geometry, and even enter play mode to inspect what it had done. The image here shows the results of that shift. Instead of only writing scripts, the agent was able to help build an actual interactive game inside Unity. At this point, it stopped feeling just like a script writer and started feeling more like an active collaborator inside the engine. Once that tool access actually existed, the next question was how far it could actually go. What happens if the agent is not only able to change things, but also able to see what it's working on and changing? What happens if it has controls designed for interacting with the game itself, not just the project files behind it? And what becomes possible when those two capabilities are actually combined? That became the main idea driving the rest of this part of the project. I added visual observation workflows, custom controls, and a benchmark environment to test whether an agent could move beyond tool use alone and begin interacting with the game more like it was a player itself. The image on this slide shows an active benchmark playthrough, which was used to test the idea in practice. In other words, this was about crossing the gap between editing a game and actually engaging with one. In the end, the agent was capable of playing the game. The benchmark results drastically varied, but the most important takeaway was that the capability itself was actually demonstrated. With the right tools, visual feedback, and controls, the agent could observe the game state, make decisions, and take in-game actions. This matters because it points to something bigger than just a single benchmark task. If an agent can play your game, then it can also help test it, evaluate it, and potentially debug it. It also suggests the possibility of agent participating in games more directly, possibly even filling in for your fourth player sometime in the future. For me, the major takeaway from this work is that the MCP style tool integration is not just a convenience feature. It meaningfully expands what an agent can do inside development workflows.
So my section focuses on one question mainly. Can an AI agent reliably manage and orchestrate complex workflows over time? So initially, I did start with a mock photogrammetry pipeline, as I talked about in the last presentation, but I ended up pivoting to a home automation because it provided a stronger stress test for sustained operation. This pivot let me evaluate not just one-time code generation, but ongoing pipeline maintenance across repeated inputs, iterative fixes, and long-running workflow behavior. So the main point of my section is about revealing an agent's reliability, orchestration, and the conditions required for consistent performance. To evaluate that research question, I ended up using a staged pipeline and ran it repeatedly under continuous input conditions. So what I was tracking was not only whether or not the task completed, but how the agent handled failures, reruns, and iterative fixes over time. Specifically, I compared behavior under tightly constrained prompts versus more ambiguous instructions. Memory assisted context was also tested to try and reduce repeated errors across iterative runs. But what I observed was that the agent could maintain orchestration across many cycles, but stability depended heavily on explicit stage contracts, clear scope boundaries, and deterministic artifact handling. So handrails were necessary to kind of keep the agent more on track to improve consistency in their behavior and in their outputs. So I would say that the strongest finding out of my research was that reliability does not come just from the agent model alone. It comes from workflow structure, so setting up stage contracts, constraining interfaces, and setting up explicit validation across all artifact outputs. And then when prompts were ambiguous, I often saw drifts and I often had to run through extra correction loops and had to encounter more inconsistent behavior from the agent. However, when the constraints were clear, the agent was able to build, maintain, and operate the pipeline much more consistently over sustained runs. So my takeaway from my section in this capstone is that practical agent autonomy is primarily a systems design problem, not just an intelligence problem.
For my part of the capstone, I focused on evaluation. My teammates' projects explored different ways agents can interact with tools, workflows, and game environments. My question was, once an agent produces something, how do we know whether it's actually good? I built a Unity-based evaluation harness around agent-generated UI. The basic task was to give agents a visual reference, then have them recreate that interface using Unity UI Toolkit. Different workflows could approach that task in different ways, but the outputs all had to become real Unity artifacts that could be loaded, previewed, and captured. So the process was, start from a reference UI, run an agent workflow, produce Unity UI Toolkit output, then capture a screenshot and generate a scorecard. The goal was to make UI generation measurable instead of relying only on subjective judgment. The scoring system had two main parts. First, it checked deterministic requirements. Did the agent create the required files? Did the UI load in Unity? Did the controller compile? And were interactions actually wired up? Second, it compared the generated screenshot against the reference using visual similarity metrics. That let the system score not only whether the output existed, but whether it visually matched the target. The result was a set of scorecards, leaderboard views, and regression reports. These made it possible to compare outputs across workflows, models, and revisions. One important piece was the feedback loop. The system didn't just score an output and stop there. If a metric was weak, that information could be fed back into the next revision prompt. For example, if the visual similarity was low, the revision brief could tell the agent to focus on color, spacing, or fine detail rather than changing unrelated code. What this revealed is that prompt quality alone was not enough. Agents performed better when the workflow gave them clear contracts: what files to produce, how to name them, how revisions should be structured, and what counted as a valid output. It also showed that visual quality and functional correctness fail in different ways. A UI can compile and respond to input, but still look wrong. Or it can look close to the reference while missing interaction logic. Treating those as separate scores made the failures much easier to understand. The broader takeaway from my part is that evaluation is what makes these agent outputs useful beyond a single demo. Once we can score them consistently, we can compare approaches, debug failures, and improve workflows over time.
So my part in this project was I tested different workflows, tasks, and specifically a different number of agents primarily. So the first task that I tried was I had a boat hull. Basically, I wanted it to generate me a mesh of a boat hull, which in this case was half a sphere with a flat plane on top. And the second task that I tried was having it generate an ocean. And this was actually pretty interesting because it revealed a difference in like more numerical, more like, yes, you can look at the file and tell that this is correct or incorrect tasks, like the mesh generation, versus you need a human or some way of processing an image in order to determine whether the output is good or not of the ocean. And on the ocean specifically, I also tested how much developer knowledge influences it. The first time that I had it try to make the ocean, I basically just told it to go ahead, gave it the little bit of knowledge I had, and it went. Versus the second run, which you can see as the lower image here, was with proper research and references, and it came out much nicer in my opinion. And so really the big takeaways from this, I think, are multiple agents with different responsibilities are good. I had 3 agents, a builder, a writer, and a reviewer, and more didn't seem to help, and having the different roles didn't seem to help that much either. So complexity is good to a point, but only to a point. You have to know what you're asking, and you have to be willing to iterate, because I mean, look at the difference between these two. So overall, our findings were that structured, well-defined workflows are best, especially multi-step workflows which help provide consistency. That access to tools means better performance. And finally, most importantly, having a good workflow is far more important than having a good prompt. Finally, we'd like to thank Professor Michael Guerrero for all his help on this project.